Waseem sir, who will give a talk on dynamics of non-equilibrium systems near critical region of phase transition.
Thank you very much. Uh, Good afternoon, everybody. My name is Waseem Bashir, and today my talk is on the dynamics of non-equilibrium systems near critical region of phase transitions. Before I start, I thank the organizers for giving me this opportunity to present my work, and also my training has been in high energy physics, so this calculation popped up when we are doing some paperwork for some other problem. So we thought that it would be better to show this to the condensed matter community so that we will check what is going on actually. So the overview is like the motivation about this and then followed by the model. And this is a general model with some some underlying symmetry properties and then over results. So what is the motivation is about, we want to understand the dynamics of non-equilibrium systems, particularly how these systems evolve with passage of time and how they equilibrate. That is the main aim. And also, we would like to know whether there are the power law behavior similar to the equilibrium phase transitions in case of these non-equilibrium phase transitions as well. The important point was to analyze if there is some underlying symmetry restoration or emergence associated with these settling down of non-equilibrium systems to the equilibrium state. So it turns out what we found was that it's indeed possible that this evolution or time evolution of this non-equilibrium system can be related to the restoration of some underlying symmetry. And for a given model with underlying U1 local gauge invariance, it turns out that if this local gauge invariance turns to the global one, then perhaps we can find out the trajectory of that, the trajectory of the system, how it equilibrates. So we have taken this analogy model from the spin systems. The figure A, first one here, it's showing a large system which is isolated, and now these spins are at very high temperature, so randomly oriented in all possible directions at having very high thermal fluctuations. Now we ask this question: what happens to this system if we allow it to expand? So it is expanding on its own, so it's the temperature of the system is coming down, and so we expect that a region which has been encircled by this blue circle, that these spins shall get correlated. If we wait long enough, then these spins must get correlated by a large amount. But because of these correlations, what we can expect is that if we somehow give some external perturbation to this spin, say this one, then this whole system should collectively behave in a proper way. So if I give external perturbation to this spin, then this one, which is already coupled to this one because of spin-spin correlations, then there must be some sort of fluctuation to that as well. So now, if we rotate this one, say we give the external fluctuation which rotates this spin, then this spin has to also cooperate in that. So it implies that if we mark this region, shown by the circle region, these 2 points, this is the center point shown by this x prime, and this boundary has been located at x. We mark this region and we call this entire region as phase locked region, where if we change any rotation, any orientation of spin in this point within the bulk, then some sort of behavior, some sort of relationship to the other spins which are lie within this region should be there. So let's consider now this model, which since I deal in high energy physics, so we took this relativistic version of this Lagrangian. This is a complex scalar field coupled with itself as well as the electromagnetic field. Now, this model has very well-known U1 local gauge invariance that's characterized by these transformation properties, that if we change this field, if we do local phase rotation on this field and simultaneously change this vector gauge field by this part, then this entire thing becomes invariant. So now, what that spin phase lock region has, what sort of effect has it on this model? That we can show that what we ask is what happens if this alpha x, which is local phase rotation, and surely it has a unique value at each space-time point. By the way, this x is the space as well as the time part. So this is a 4 vector. what happens if in the, I will show the previous slide. What happens if we choose the local phase having some relationship? Say if it was alpha x prime here, say alpha x here. What happens if we choose some relationship between that phase angle? What happens to our model then? It turns out that if we choose this sort of relationship between the phase angles, this is at the bulk and this one is at the boundary, and use this power law, then with R some parameter, which we don't know what actually it is, but just we took it. And for this constant value of this R, now the field at the boundary can be related to the bulk. So it turns out this, it can be related, this is the field which is at the boundary, and this one is at the bulk. So, sorry, this one is at the boundary, and this one is the bulk, and this is the relationship between them. Okay, so now if we choose in the limiting case, so once we take that region which we encircled, if we take that very small, then in that limiting case we get this differential equation, and for this right hand side, if we take this very small, then we end up getting this diffusion equation in time-dependent random potential. So this one we obtain. Okay, so now whatever the equation is, if this is correct, then it should surely yield the correct description for the order parameter. Once the system goes to the equilibrium, it should at least tell us how order parameter should behave with time. So what we do is, we took the first case where we didn't take any external perturbation, so that was shown by this gauge field going to 0, then, and we took the Fourier transform of this. What we found was this is the differential equation, a simple differential equation, and once we found the order parameter for the constant value of this dissipation coefficient, it turns out that the behavior of this m, which is order parameter, is governed by this power law, which is 1 by t to the power half, which is a very well known result. So this one we got essentially by claiming that the phase angle, the local gauge in that region has broken, and you are restoring the local gauge to global within that boundary. Okay, so now if we move to the other case where we take this gauge field in the mean field approximation, we take this time-dependent part to be constant, then the equation of motion turns out to be this much, where E is the charge on the complex that's represented by complex field, R is that element, and B is the scaling factor which we have used. And then it turns out the order parameter in this case turns out to be that 1 by t to the power half, but it's stretched by this exponential factor. If we plot the real part, if we plot this m of t, the real part of this, then it turns out to be that's fluctuating, even though the amplitude is still governed by this universal law, that's 1 by t to the power half. These all results are valid if we take the dissipation, this was taken to be constant. If we change it to be time dependent, then these results are modified. Then the earlier one, yes, once again, this one changed to 1 by 3, the power goes to 1 by 3, and so on. This result also will change. But the only thing which we wanted to show was that these results perhaps can be shown to be governing from some underlying symmetry restoration processes. How this goes once you want to restore maybe some higher symmetry group, we have not done that part of calculation, but this much we wanted to show. Thank you very much. I'm thankful to the ICTS-TIFR Bengaluru for when I was here at this time. These are some, and thank you.
Questions? If there is no questions, let's thank the speaker again.